What if the ticking of your clock, the beating of your heart, the very passage of each second depends not on some universal cosmic timekeeper, but on how fast you're moving through space? This isn't a thought experiment from a philosopher's armchair. This is reality, verified by countless experiments, confirmed by technologies you use every day, and woven into the very fabric of our universe. Today, we're diving deep into one of nature's most mind-bending secrets. Why does time itself slow down as you approach the speed of light? For most of human history, we assume time was absolute. Isaac Newton, whose laws of motion governed physics for over 2 centuries, believed in a universal clock ticking away in the background of reality. Every event in the universe, whether happening on Earth or in a distant galaxy, occurred within this single, uniform flow of time. A second was a second, everywhere and for everyone. This made intuitive sense. When you're sitting in a cafe and your friend is jogging in the park, you both experience the same afternoon. The sun sets at the same moment for both of you. Your watches stay synchronized. Time seems utterly democratic, treating all observers identically regardless of what they're doing or how they're moving. But nature had a stunning surprise waiting for us, hidden in the properties of light. In 1887, 2 American physicists named Albert Michelson and Edward Morley conducted what would become one of the most famous failed experiments in scientific history. They were trying to detect the luminiferous ether, a hypothetical substance through which light was thought to travel, much like sound travels through air. Their experiment was elegant and precise. They reasoned that as Earth orbited the Sun at about 30 kilometers per second, it should be moving through this cosmic ether like a boat through water. Light traveling in the direction of Earth's motion should appear slower, while light traveling perpendicular should appear faster. The difference would reveal the ether's existence. But to everyone's astonishment, they found no difference at all. Light traveled at exactly the same speed regardless of direction. No matter how Earth moved through space, no matter what direction they shone their light, the result was always the same. The speed of light seemed constant, immutable, independent of the observer's motion. This was deeply puzzling. In everyday experience, speeds always add up. If you're walking forward on a moving train, an observer on the platform sees you moving faster than the train alone. But light didn't behave this way. A beam of light from a moving flashlight traveled at the same speed as one from a stationary flashlight. Something was fundamentally wrong with our understanding of motion itself. Enter Albert Einstein, a 26-year-old patent clerk in Switzerland with an extraordinary gift for thought experiments. In 1905, he published a paper titled "On the Electrodynamics of Moving Bodies" that would revolutionize physics forever. Einstein took the Michelson-Morley results seriously. Instead of trying to explain away the constancy of light speed, he embraced it as a fundamental principle of nature. Einstein proposed 2 postulates that would form the foundation of special relativity. First, the laws of physics are the same for all observers moving at constant velocity relative to each other. Second, the speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or observer. These might sound simple, even obvious, but their consequences are anything but. If the speed of light is truly constant for all observers, then something else must give. And that something else is time itself. Einstein showed mathematically that if 2 observers are moving relative to each other, they will disagree about the passage of time. Not because their clocks are faulty or their measurements imprecise, but because time itself flows at different rates for different observers. This is time dilation, the stretching of time due to relative motion. The faster you move relative to another observer, the slower your clock ticks compared to theirs. And as you approach the speed of light, this effect becomes increasingly dramatic. At 90% light speed, your clock ticks about half as fast as a stationary clock. At 99% light speed, it ticks about 7 times slower. At 99.999% light speed, it ticks over 22 times slower. But wait, how can this be? Surely if I'm moving and you're stationary, I should experience my own time normally while your clock appears slow to me. And you should experience your time normally while my clock appears slow to you. Doesn't this create a contradiction? This apparent paradox lies at the heart of relativity's counterintuitive nature. And here's the beautiful resolution. Both perspectives are equally valid. There's no absolute truth about whose clock is really running slower. From your reference frame, my clock is slow, From my reference frame, your clock is slow. Neither of us is wrong. Time itself is relative to the observer. This might sound like philosophical wordplay, but it has real, measurable consequences. The paradox only seems contradictory because we're clinging to Newton's idea of absolute time. Once we accept that time is woven together with space into a unified fabric called spacetime, the apparent contradiction dissolves. Different observers simply take different paths through spacetime, and different paths have different durations. Think of it this way. Imagine two cities connected by two different roads. One road goes straight between them, while the other curves around a mountain. A driver on the straight road travels less distance than one on the curved road, even though both start and end at the same points. In spacetime, moving objects take different paths through the temporal dimension, and those paths have different lengths measured in time rather than distance. Let me give you a concrete example that makes this visceral. Imagine you have a twin sibling. On your 20th birthday, your twin boards a spacecraft and accelerates to 99% the speed of light, traveling to a star 10 light-years away and back. From Earth's perspective, the round trip takes a bit over 20 years. When your twin returns, you're celebrating your 41st birthday, gray hair appearing at your temples, wrinkles forming around your eyes. But your twin steps off the spacecraft looking barely older than when they left. For them, only about 3 years have passed. They're now 23 while you're 41. You've aged nearly 2 decades more than your sibling. This isn't fantasy or metaphor. It's the genuine prediction of special relativity, and we've verified it with extraordinary precision using particle accelerators and atomic clocks. By the way, if you're enjoying diving this deep into the nature of time and space, you'd probably love the other cosmic mysteries we explore on this channel. Make sure to subscribe and turn the notification bell so you don't miss the next mind-bending journey through the universe. Trust me, what we're discovering about reality these days is stranger than any science fiction. Now, you might be wondering, if objects experience time differently based on their motion, does this mean the speed of light represents some kind of ultimate cosmic speed limit? This connects to something absolutely fascinating about our universe. If you're curious about whether anything can actually exceed light speed, and what that would mean for our understanding of reality, I made a detailed video exploring exactly that question called, "Is the speed of light really the fastest speed in the universe?" I dive deep into apparent violations, quantum weirdness, and cosmic loopholes that might surprise you. Check it out after this one. The link is in the description and on the card above. But back to time dilation. Let's understand why this happens, not just accept that it does. The key insight involves something called a light clock, a beautifully simple thought experiment that reveals relativity's core truth. Imagine a clock that works by bouncing a single photon of light between two mirrors, one at the top and one at the bottom. Each time the photon completes a round trip, the clock registers one tick. It's the simplest possible timekeeper, relying only on light's constant speed. Now picture this clock sitting stationary beside you. The photon bounces straight up and down, traveling a fixed distance with each tick. The time between ticks depends on how far the photon must travel divided by its speed. Simple and predictable. But what happens if this clock zooms past you at tremendous velocity? From your perspective, something fascinating occurs. The photon still bounces between the mirrors, but now it has to travel diagonally. While moving up to reach the top mirror, the clock itself has moved sideways. The photon must chase the mirror, taking a longer diagonal path rather than a straight vertical one. Here's where the magic happens. The speed of light is constant for all observers. This means the photon in the moving clock travels at exactly the same speed as the photon in your stationary clock. But the moving clock's photon must cover a longer diagonal distance with each bounce. If the speed is the same but the distance is longer, the time between ticks must be greater. The moving clock literally ticks slower than yours. Not because anything is wrong with it, not because of some mechanical effect of motion, but because light must travel a longer path between each tick. Time itself stretches for the moving clock. The mathematics works out beautifully. The factor by which time slows down is given by the Lorentz factor, named after Dutch physicist Hendrik Lorentz, who discovered these equations before Einstein explained their physical meaning. The Lorentz factor equals 1 divided by the square root of 1 minus v squared over c squared, where v is velocity and c is the speed of light. When you're moving slowly compared to light, v squared over c squared is tiny, and the Lorentz factor is essentially 1. Time passes normally. But as v approaches c, that fraction approaches 1, making the denominator approach 0, making the Lorentz factor approach infinity. Time dilation becomes infinite at light speed, meaning time would completely stop for anything traveling at that velocity. This immediately tells us something profound. Nothing with mass can actually reach light speed. As you accelerate towards c, time slows down more and more, but it would take infinite energy to reach c itself. The speed of light isn't just the speed limit imposed by cosmic traffic laws. It's woven into the structure of spacetime itself. Photons, which do travel at light speed, experience no time at all. From a photon's perspective, if we can even speak of such a thing, it is emitted and absorbed in the same instant. A photon leaving a distant galaxy and arriving at your eye billions of years later experiences its entire journey as instantaneous. For light, there is no duration, no before and after, no past or future. Light exists in an eternal present. This is almost impossible to truly comprehend because our entire experience is built around the passage of time. We remember the past, anticipate the future, and exist in an ever-moving present. But for a photon, these categories simply don't apply. The light that left a supernova 10,000 years ago and is just now reaching Earth has, from its own perspective, made an instantaneous journey. It departed and arrived simultaneously. The billions of years we measure are purely from our time-bound reference frame. Let's move from thought experiments to cold, hard evidence. Has time dilation actually been measured? Absolutely, and the confirmations are stunning in their precision and variety. The first direct test came in 1971 when physicists Joseph Haffel and Richard Keating placed cesium atomic clocks on commercial airplanes and flew them around the world, some eastward and some westward. These clocks were accurate to nanoseconds, billionths of a second. When they returned and compared them to identical clocks that had stayed on the ground, the differences were exactly what Einstein's equations predicted. The eastward flying clocks, moving faster relative to Earth's surface because they added to the planet's rotation, ran slightly slower. The westward flying clocks, moving slower relative to Earth's surface, ran slightly faster. The measured time differences were mere hundreds of nanoseconds, but they matched relativity's predictions with remarkable accuracy. Time dilation is real, measurable, and exactly described by Einstein's century-old equations. But that was just the beginning. Today, we have far more precise tests. The global positioning system that guides your phone's maps relies fundamentally on relativistic corrections. GPS satellites orbit Earth at about 14,000 kilometers altitude, moving at roughly 4 kilometers per second. At these speeds, special relativistic time dilation makes their clocks tick about 7 microseconds slower per day compared to clocks on Earth's surface. But there's another effect at play, gravitational time dilation, which we'll explore shortly. Being higher in Earth's gravitational field makes the satellite clocks tick faster by about 45 microseconds per day. The net effect is that GPS clocks gain about 38 microseconds daily compared to ground clocks. Without correcting for both relativistic effects, GPS positions would drift by roughly 10 kilometers per day. The fact that GPS guides you accurately to within a few meters is continuous proof that relativity works. Particle accelerators provide even more dramatic confirmation. At facilities like CERN's Large Hadron Collider near Geneva, particles are accelerated to 99.999999% the speed of light. At these velocities, time dilation factors exceed 7,000. Unstable particles that normally decay in microseconds survive for milliseconds in the lab frame because their internal clocks are running thousands of times slower. Muons offer a particularly beautiful example. These elementary particles are created when cosmic rays strike atoms in the upper atmosphere, about 10 kilometers above Earth's surface. Muons are unstable, decaying with a half-life of about 2.2 microseconds. Moving at nearly light speed, they should travel only about 660 meters before half of them decay. By the time they reach sea level, virtually none should survive. yet we detect enormous numbers of muons at ground level. How is this possible? Time dilation. From our perspective, the muons' internal clocks run slow because of their tremendous speed. Their 2-microsecond half-life stretches to tens of microseconds in our reference frame, giving them plenty of time to reach Earth's surface. We are literally seeing particles living longer because time passes more slowly for them. From the muon's perspective, something equally interesting happens. The muon experiences its normal 2-microsecond lifetime, so how does it cover the distance? The answer is length contraction. Space itself compresses in the direction of motion. From the muon's viewpoint, the 10-kilometer distance between the upper atmosphere and Earth's surface shrinks to mere hundreds of meters. Both perspectives are valid, and both preserve the constancy of light speed. This reciprocity between time dilation and length contraction reveals something profound about the nature of spacetime. Space and time aren't separate entities that exist independently. They're interwoven aspects of a single four-dimensional fabric. When you move through space faster, you move through time slower. Your total speed through spacetime remains constant, but its distribution between spatial and temporal components shifts with your velocity. Imagine spacetime as a pie that you're always eating at a constant rate. When you're sitting still, you're consuming the pie entirely from the time slice. You're moving through time at maximum rate, but through space not at all. As you start moving through space, you have to take some of your eating from the time slice and apply it to the space slice. You're moving through space now, but more slowly through time. At very high speeds, almost all your eating goes to the space slice, leaving barely any for time. You're racing through space while barely crawling through time. At light speed, the entire pie would be space slice. Maximum movement through space, zero movement through time. This is why time stops at light speed, and why nothing with mass can get there. This geometric picture of spacetime was developed by Einstein's former mathematics professor Hermann Minkowski, who famously declared in 1908, "Henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." Minkowski's spacetime diagrams provide powerful visual tools for understanding relativistic effects. In these diagrams, time runs vertically and space runs horizontally. A stationary object traces a vertical line, moving through time, but not space. A moving object traces a tilted line, and the faster it moves, the more tilted toward horizontal its path becomes. Light rays travel at 45-degree angles, representing the maximum tilt, the boundary between paths that are possible for massive objects and paths that aren't. The geometry of these diagrams reveals why time dilation occurs. Different observers draw different coordinate grids on spacetime, with their time axes aligned along their own motion. What one observer measures as pure time, another observer measures as a mixture of space and time. Simultaneity itself becomes relative. Events that happen at the same time for one observer happen at different times for another. This relativity of simultaneity is perhaps the most mind-bending consequence of Einstein's theory. Imagine a train car with a light bulb exactly in its center. When the bulb flashes, light travels outward toward both ends of the car. For a passenger on the train, the light reaches both ends simultaneously. After all, both ends are equidistant from the center, and light travels at the same speed in both directions. But for an observer on the platform watching the train speed past, something different happens. The rear of the train is moving toward the expanding light sphere, while the front is moving away from it. Since light travels at the same speed for all observers, the light reaches the rear of the train before it reaches the front. Events that were simultaneous for the train passenger are sequential for the platform observer. Neither observer is wrong. Both are correctly describing reality from their reference frame. Simultaneity itself depends on your state of motion. This has staggering implications. It means there's no universal now extending across the cosmos. Your present moment is different from the present moment of someone moving relative to you. The universe doesn't have a single present. It has infinitely many presents, one for each possible state of motion. This brings us to questions about the nature of existence itself. If my now is different from your now, does that mean events in my future already exist from your perspective? Does the past still exist? Is the future already determined? Physicists and philosophers have debated these questions for over a century, and there's still no consensus. The block universe interpretation suggests that all of space-time exists eternally, with past, present, and future equally real. Time doesn't flow, we simply experience successive slices of an already existing four-dimensional structure. Our sense of moving through time is an illusion created by how our consciousness processes the block universe. Others reject this view, arguing that the present has a special status and the future remains genuinely open. They point out that experiencing time's passage is fundamental to consciousness, and dismissing it as illusion seems to ignore something essential about reality. The debate continues, touching on questions of free will, determinism, and the nature of existence itself. What we can say with certainty is that time dilation is real and measurable. Whatever the philosophical interpretation, clocks in relative motion genuinely tick at different rates. Twins really do age differently when one takes a high-speed journey. Particles really do live longer when moving fast. The equations work, the predictions are confirmed, and the technology based on relativity functions flawlessly. Now let's explore another dimension of time dilation: gravitational time dilation, predicted by Einstein's general theory of relativity, published in 1915, a decade after special relativity. While special relativity deals with motion, general relativity deals with gravity, and it reveals that gravitational fields also warp time. Einstein's key insight was the equivalence principle. There's no experiment you can perform to distinguish between being in a gravitational field and being in an accelerating reference frame. If you're in an elevator with no windows, you can't tell whether you're stationary on Earth's surface feeling normal gravity or in deep space accelerating at 10 meters per second squared. Both feel identical. This equivalence has profound implications. If acceleration affects time, which special relativity tells us it does, then gravity must also affect time. Clocks in stronger gravitational fields tick slower than clocks in weaker fields. Near massive objects like planets, stars, or black holes, time passes more slowly than far away in empty space. This isn't just theory. Gravitational time dilation has been measured with exquisite precision. In 1976, NASA launched Gravity Probe A, carrying a hydrogen maser clock to an altitude of 10,000 kilometers. The clock ran faster than identical clocks on Earth's surface by exactly the amount general relativity predicted, about 4 parts in 10 billion. More recently, optical atomic clocks have become precise enough to detect gravitational time dilation over height differences of just 30 centimeters, roughly 1 foot. Clocks on a table tick measurably faster than clocks on the floor because they're slightly further from Earth's center and thus in a slightly weaker gravitational field. The difference is incredibly tiny but absolutely real and measurable. Consider what this means for everyday life. Your head ages slightly faster than your feet because it's further from Earth's center. Over an 80-year lifetime, your head ends up about 90 billionths of a second older than your feet. The difference is imperceptible to human experience, but it's genuine. Time itself flows at different rates across the height of your own body. Black holes represent the extreme case of gravitational time dilation. These cosmic monsters have such intense gravity that at their event horizons, the point of no return, gravitational time dilation becomes infinite. To an outside observer, a clock falling toward a black hole appears to tick slower and slower as it approaches the event horizon, never quite crossing it. Time grinds to a complete halt at the horizon from the external perspective. From the falling clock's perspective, things look very different. It crosses the event horizon in finite time, experiencing no special moment at the boundary. The clock continues ticking normally by its own measure, even as it plunges toward the singularity at the black hole's center. This asymmetry between external and falling observers creates fascinating paradoxes that physicists are still working to fully understand. The movie Interstellar, advised by Nobel Prize-winning physicist Kip Thorne, dramatized gravitational time dilation beautifully. When astronauts visit a planet orbiting close to a supermassive black hole, they experience severe time dilation. 1 hour on the planet's surface corresponds to 7 years passing on their spacecraft orbiting further away. The emotional weight of this scene, a father watching his children age decades while he experiences mere hours, captures something profound about relativity's implications for human existence. This isn't artistic license. The mathematics checks out. Near a black hole of sufficient mass, such extreme time dilation is entirely possible. Kip Thorne worked closely with the filmmakers to ensure the portrayal was scientifically accurate, and the resulting black hole visualization became the most realistic ever created for cinema. Now let's connect these two forms of time dilation, velocity-based and gravitational, into a unified picture. Einstein's general relativity reveals that both effects arise from the same underlying cause: the geometry of spacetime itself. Mass and energy curve spacetime, and moving through curved spacetime at different speeds means tracing different paths with different durations. The GPS satellites I mentioned earlier experience both effects simultaneously. They're moving fast enough that special relativistic time dilation slows their clocks, but they're also high enough in Earth's gravitational well that gravitational time dilation speeds their clocks up. Engineers must account for both effects to achieve accurate positioning. It's a daily practical application of Einstein's century-old theories. But why does spacetime have this particular geometry? Why does moving through space affect passage through time? This is where we approach the edges of current understanding. Einstein's equations describe how spacetime curvature relates to mass and energy, but they don't explain why the universe has this structure. That's simply how nature appears to work. Some physicists believe a deeper theory, perhaps quantum gravity or string theory, will eventually explain why spacetime behaves as it does. Others suspect the question might be unanswerable, like asking why the universe exists at all. What we can say is that time dilation isn't an arbitrary quirk, but emerges necessarily from the principle that light speed is constant for all observers. Given that single starting point, all of special relativity follows mathematically. The constancy of light speed itself might seem arbitrary, but it connects to deep features of electromagnetism and quantum field theory. Light is an electromagnetic wave, and the speed of these waves depends on fundamental constants: the electric permittivity and magnetic permeability of free space. These constants determine how electric and magnetic fields interact, and their values set light speed at precisely 299,792 kilometers per second. More profoundly, modern physics views the speed of light not as the speed of one particular thing, but as the maximum speed at which causality can propagate through the universe. It's the speed limit for any influence, any information, any connection between events. Gravity waves travel at this speed. Changes in electromagnetic fields propagate at this speed. Any massless particle moves at this speed. Light just happens to be the most familiar example. This cosmic speed limit preserves causality, the principle that causes must precede their effects. If information could travel faster than light, different observers would disagree about the order of events. Some would see effect before cause, enabling paradoxes like receiving an answer before sending a question. The speed of light protects the logical consistency of the universe. Time dilation is intimately connected to this causal structure. As you approach light speed, time slows down precisely because faster than light travel would violate causality. The mathematics of special relativity doesn't just describe time dilation. It explains why the universe must work this way to remain self-consistent. Let's explore what happens at the quantum level, where relativity meets the strange world of subatomic particles. Quantum field theory, which underlies our best understanding of particle physics, is fully compatible with special relativity. In fact, the marriage of quantum mechanics and special relativity proved extraordinarily fruitful, predicting antimatter and explaining countless particle phenomena. Paul Dirac achieved this synthesis in 1928 when he wrote down an equation describing electrons that respected both quantum mechanics and special relativity. The Dirac equation made a stunning prediction. For every particle, there must exist a corresponding antiparticle with opposite charge. For years later, Carl Anderson discovered the positron, the electron's antiparticle, in cosmic ray experiments, confirming Dirac's prediction and demonstrating the power of relativistic quantum theory. Time dilation affects quantum processes just as it affects classical ones. Radioactive decay, for example, is governed by quantum mechanical probabilities. A radioactive nucleus has a certain probability of decaying in any given time interval. When such nuclei are accelerated to high speeds, we observe them decaying more slowly in the laboratory frame. Their quantum clocks, like all clocks, experience time dilation. The standard model of particle physics, our best theory of fundamental particles and forces, is built entirely within the framework of relativistic quantum field theory. Every prediction it makes, and it has made thousands, verified to extraordinary precision, assumes that special relativity holds at the quantum level. Time dilation is woven into the fabric of our most successful physical theory. Experiments at particle accelerators continuously confirm these predictions. At the Large Hadron Collider, particles collide at energies that were present in the universe only a trillionth of a second after the Big Bang. The behaviors observed match relativistic quantum predictions perfectly. Time dilation factors of thousands are routine, and the data confirms Einstein's equations with ever-increasing precision. But challenges remain at the intersection of relativity and quantum mechanics. General relativity, Einstein's theory of gravity, has not yet been successfully merged with quantum mechanics. The two frameworks use different mathematical languages and make conflicting assumptions about the nature of space and time. Resolving this conflict is one of the great unsolved problems in theoretical physics. String theory and loop quantum gravity represent two leading approaches to quantum gravity. String theory proposes that fundamental particles are tiny vibrating strings with different vibration patterns corresponding to different particles. Loop quantum gravity suggests that spacetime itself is quantized, composed of discrete chunks at the smallest scales rather than being continuous. Both approaches preserve the essential features of relativity, including time dilation, while attempting to extend physics to realms where current theories break down. The Planck scale marks the frontier where quantum gravity effects become important. At distances of about 10 to the negative 35 meters and times of about 10 to the negative 43 seconds, both quantum mechanics and gravity are essential. These scales are almost inconceivably tiny. The Planck length is to an atom as an atom is to the observable universe. No experiment has yet probed these scales directly, so quantum gravity remains theoretical. What might time dilation look like at the Planck scale? We honestly don't know. Some theories suggest that space-time might become foamy at these scales, with quantum fluctuations creating temporary tiny black holes and wormholes. Others propose that time itself might become discrete, flowing not continuously but in tiny jumps. Until we can test these ideas experimentally, they remain informed speculation. Let's return to larger scales and explore some remarkable consequences of time dilation that stretch the imagination. Consider what happens if you could accelerate continuously at 1 Earth gravity, a comfortable acceleration that would feel just like standing on our planet's surface. Starting from rest and accelerating at 10 meters per second squared, how far could you travel? The mathematics yields astonishing results. After 1 year of ship time, 12 months of your personal experience, you'd be traveling at 99.9% light speed and would have covered about half a light year. After 2 years of ship time, you'd be covering more than 3 light years. After 10 years of ship time, you'd be approaching 10,000 light years of distance, nearly a tenth of the way across our galaxy. By the time 20 years of ship time passed, you'd have crossed the entire Milky Way galaxy, 100,000 light years from edge to edge. Yet on Earth, about 100,000 years would have elapsed. Your great-grandchildren would be ancient history, their descendants spread across thousands of generations. Civilizations would have risen and fallen while you experienced just 2 decades. Continue accelerating for 30 years of ship time, and you'd leave the local group of galaxies, millions of light years from home, with millions of years passing on Earth. After 50 years of ship time, still potentially within a human lifespan, you'd have crossed billions of light years, traveling deep into the observable universe, while billions of years elapsed back home. This thought experiment reveals something wonderful and terrible about relativistic travel. Wonderful because the universe is, in principle, accessible to human exploration within single lifetimes. A crew leaving Earth could cross galaxies and return, having aged only decades. Terrible because they would return to a future so distant that nothing familiar would remain. Their home would be unrecognizable, everyone they knew dead for millions or billions of years. The practicalities are currently impossible, of course. Maintaining one gravity of acceleration requires enormous amounts of energy. The fuel needed exceeds the mass of the spacecraft by factors that boggle comprehension. Shielding against radiation and interstellar dust at near-light speeds presents unsolved engineering challenges. But the physics itself permits such journeys. The universe doesn't forbid us from crossing galaxies in a human lifetime. It only makes it extraordinarily difficult. Science fiction has explored these themes extensively. Authors like Alastair Reynolds, Joe Haldeman, and Ursula K. Le Guin have written profound stories about the human consequences of relativistic travel. In Haldeman's The Forever War, soldiers fighting an interstellar conflict return home after subjective months to find centuries have passed. Society has transformed beyond recognition, and they're strangers in their own world. These stories capture the emotional weight of time dilation in ways that equations cannot. Now let's consider time dilation from a cosmological perspective. The universe itself is expanding, carrying galaxies apart like dots on an inflating balloon. Light from distant galaxies is redshifted, stretched to longer wavelengths, because space itself has expanded during the light's journey. This expansion affects time as well, connecting to time dilation in subtle ways. When we observe a distant supernova, an exploding star, we're not just seeing light from the past. We're seeing light that has been stretched by cosmic expansion. The supernova's light curve, which normally rises and falls over weeks, appears stretched out when the supernova is billions of light years away. A supernova that would take 20 days to fade nearby takes 40 days to fade when observed at a redshift of 1, meaning the universe has doubled in size since the light was emitted. This cosmological time dilation is directly observed and matches predictions perfectly. It's yet another confirmation that our understanding of spacetime, local and cosmic, special and general relativistic, correctly describes nature. The equations Einstein wrote in his small apartment over a century ago continue to pass every test we throw at them. The cosmic microwave background radiation provides another window into cosmological time dilation. This radiation, the afterglow of the Big Bang, was emitted about 380,000 years after the universe began. It has been traveling through expanding space for over 13 billion years. The radiation we detect today started as visible light, but has been stretched to microwave wavelengths, redshifted by a factor of about 1,000. Any processes that were happening when this radiation was emitted would appear time-dilated to us by the same factor. If there were cosmic clocks ticking back then, and in a sense, atomic and nuclear processes provided such clocks, they would appear to tick 1,000 times slower from our perspective. The early universe, as we observe it, seems frozen in slow motion. Looking forward instead of backward, what does the far future hold for time itself? As the universe continues expanding, driven by the mysterious dark energy that pervades space, distant galaxies will recede faster and faster. Eventually, they'll cross the cosmic horizon, the boundary beyond which light can never reach us. One by one, galaxies will disappear from view, their light stretched to infinity, their time appearing to freeze at the horizon. In the extremely distant future, trillions of years from now, observers in our galaxy may see an apparently static universe. All other galaxies will have faded beyond detection. The cosmic microwave background will have redshifted to undetectable wavelengths. Evidence of the Big Bang, of cosmic expansion, of the larger universe, will have disappeared. Future astronomers might conclude they live in an island of matter in an infinite void, unaware of the cosmic history written in light that can no longer reach them. This is the ultimate time dilation, the entire external universe appearing frozen at distant horizons, its time slowed to an apparent stop by the relentless expansion of space. The universe will effectively hide its own past from future observers, erasing the evidence of its explosive origin and dynamic youth. These cosmological perspectives remind us that time dilation isn't just a local phenomenon affecting fast-moving particles or spacecraft. It's woven into the structure of the cosmos at the largest scales, shaping how we observe the universe and how the universe will appear to observers in the far future. But let's bring things back to the human scale and consider what time dilation means for our understanding of reality itself. We experience time so directly, so continuously, that it's hard to accept its relative nature. Our entire psychology is built around temporal experience. Memories of the past, anticipation of the future, the vivid sense of an ever-present now. How can something so fundamental to consciousness be observer-dependent? Philosophers have grappled with this question for millennia, long before Einstein made it scientifically precise. Ancient thinkers like Augustine of Hippo wondered about time's nature, famously writing, "What then is time? If no one asks me, I know what it is. If I wish to explain it to him who asks, I do not know." Einstein's relativity didn't answer the philosophical question of what time is, but it radically constrained the possible answers. We now know that any adequate theory of time must account for its relativity. Time cannot be an absolute background against which events unfold. It must somehow emerge from or be intertwined with the physical world. Different observers experiencing different times isn't a failure of measurement. It's a feature of reality itself. Some neuroscientists and philosophers argue that our perception of time flowing is a construction of consciousness rather than a direct perception of reality. The brain processes information sequentially, creating memories, updating predictions, generating the experience of duration. But this psychological time might not correspond to anything fundamental in physics. The equations of physics, both classical and quantum, are time-symmetric. They work equally well running forward or backward. The asymmetry we experience, the fact that we remember the past but not the future, that eggs break but don't unbreak, that we age rather than grow young, comes not from the fundamental laws but from special initial conditions. The universe began in an extraordinarily low entropy state at the Big Bang, and entropy has been increasing ever since. This thermodynamic arrow of time creates the asymmetry we experience, but it's not built into the basic equations. Time dilation adds another layer to this mystery. If two observers can disagree about the duration between events, about what happens simultaneously, about the order of spatially separated events, then the simple picture of time as a river flowing from past to future becomes untenable. Time is something more subtle, more geometric, more dependent on perspective than our everyday experience suggests. Let me share something that continues to astonish physicists and philosophers alike: the block universe interpretation I mentioned earlier. In this view, the past, present, and future all exist equally. The universe is a four-dimensional structure in which time is just another dimension, like the three spatial ones. We experience time sequentially because of how our consciousness moves through the block, but the entire structure, all of history and all of the future, exists timelessly. From this perspective, time dilation isn't really time slowing down. It's different observers slicing the block universe at different angles. Just as two people cutting a loaf of bread at different angles get different shaped slices, observers in relative motion slice spacetime at different angles, getting different presents that include different sets of events as simultaneous. This interpretation is controversial. Many physicists accept it as the most natural reading of relativity's mathematics. Others find it philosophically troubling because it seems to undermine free will and the openness of the future. If the future already exists in the same sense the past does, how can our choices be genuinely free? Are we merely discovering our predetermined paths through the block rather than creating them? These questions don't have scientific answers. They're metaphysical interpretations of the mathematical formalism. What science can tell us is that whatever time ultimately is, it behaves according to Einstein's equations. Clocks in relative motion really do tick at different rates. Twins really do age differently when one travels at high speed. These are experimental facts, not philosophical positions. Now let's explore some of the stranger implications of time dilation that scientists have seriously considered. If time slows down as you approach light speed and stops at light speed, what would happen if you could somehow exceed light speed? Setting aside the physical impossibility, the mathematics suggests something bizarre. Time would run backward. Faster than light travel, if it were possible, would be equivalent to time travel into the past. This is because the same Lorentz transformation equations that describe time dilation also describe how different observers relate events in space and time. For a faster-than-light signal, some observers would see the signal arriving before it was sent. Effect would precede cause. This isn't just a mathematical curiosity. It's a deep reason why physicists believe faster-than-light travel is truly impossible. not just practically difficult. A universe that allowed backward-in-time travel would face logical paradoxes. You could send a message to your past self telling you not to send the message. Such contradictions suggest that nature forbids faster-than-light travel to protect its own logical consistency. Wormholes, hypothetical tunnels through spacetime, offer another potential route to time travel. If you could create a wormhole connecting two distant points in space, then accelerate one end to high velocity and bring it back, time dilation would cause less time to pass at the moving end. The two ends would then connect points in spacetime at different times as well as different places. Step through the wormhole, and you'd emerge in your own past. Kip Thorne and his colleagues analyzed this possibility in detail in the 1980s, concluding that while general relativity permits such configurations, quantum effects might intervene to prevent actual time travel. Stephen Hawking proposed the chronology protection conjecture, the idea that nature conspires to prevent time machines, perhaps through the buildup of quantum fluctuations that would destroy any nascent time machine before it could operate. Whether time travel is truly impossible or merely extraordinarily difficult remains an open question. What we can say is that time dilation itself is real, and its extreme cases approach the boundaries of time travel. A journey at 99.999% light speed to a star 10 light-years away and back might take only a few months of ship time, while decades pass on Earth. This is one-way time travel into the future, perfectly possible within known physics. If you're finding this journey through space-time as fascinating as I do, make sure to subscribe to the channel and give a thumbs up. I explore these cosmic mysteries regularly, and having you along for the ride means more than you know. The twin paradox has a resolution worth exploring in more depth. If motion is relative, why does the traveling twin age less? Why isn't the situation symmetric, with each twin claiming the other's clock is slow? The answer lies in acceleration. The traveling twin must accelerate to leave Earth, decelerate in reverse direction at the destination, then accelerate again to return home. These accelerations break the symmetry between the twins. During the constant velocity portions of the journey, each twin indeed sees the other's clock running slow. But during the turnaround acceleration, something dramatic happens from the traveling twin's perspective. The distant twin's clock suddenly runs extremely fast, making up for all the lost time, and then some. When properly calculated using either special or general relativity, both twins agree on the final result. The traveler has aged less. This resolution highlights how acceleration and gravity, which Einstein showed are equivalent, connect to time dilation. The traveling twin experiences acceleration during the journey, and this acceleration causes additional time dilation effects that break the apparent paradox. Clocks in accelerating reference frames run at different rates depending on their position relative to the acceleration direction. This equivalence between acceleration and gravity has practical consequences. In a rotating reference frame, like a spinning space station, points further from the axis experience greater acceleration. Clocks at these outer points tick slower than clocks near the axis. This effect is tiny for human-scale rotating structures, but it's measurable with sufficiently precise instruments and must be considered in high-precision experiments. The gravity probe, an experiment I mentioned earlier, measured gravitational time dilation directly. A more ambitious experiment, Gravity Probe B, launched in 2004 to test another prediction of general relativity: frame dragging, the tendency of massive rotating objects to twist spacetime around them. Both experiments confirmed Einstein's predictions with spectacular precision, adding to the mountain of evidence supporting relativistic time effects. Let's delve deeper into black holes, those cosmic laboratories where time dilation reaches its most extreme. A black hole is defined by its event horizon, the boundary within which escape velocity exceeds light speed. At the event horizon, gravitational time dilation becomes infinite. An external observer watching an object fall toward a black hole would see it slow down asymptotically, never quite reaching the horizon. The object would appear to freeze at the boundary, its image redshifting toward invisibility. But from the falling object's perspective, nothing special happens at the event horizon. It crosses infinite time by its own clock, continuing to fall toward the singularity at the center. The object experiences extreme tidal forces, different parts of it being pulled with different strengths, but time passes normally from its internal perspective. The infinite time dilation exists only in the external observer's view. This asymmetry between external and falling perspectives creates deep puzzles about the nature of information. When something falls into a black hole, what happens to the information it contains? From outside, the object seems frozen at the horizon forever, its information apparently preserved there. From the falling perspective, it crosses the horizon and reaches the singularity, where known physics breaks down. Stephen Hawking discovered in 1974 that black holes aren't perfectly black. They emit radiation through quantum effects near the event horizon. This Hawking radiation causes black holes to slowly evaporate over astronomical timescales. A solar mass black hole would take about 10 to the 67 years to evaporate, far longer than the current age of the universe. But the evaporation raises a profound question. What happens to the information about everything that fell in? Hawking initially argued that the information was lost, destroyed when the black hole evaporated. This would violate quantum mechanics, which demands that information is conserved. The resulting black hole information paradox has driven theoretical physics for decades, with proposed resolutions involving exotic ideas like holography, firewalls, and quantum entanglement across horizons. Recent work, particularly by physicists like Meldesena and Leonard Susskind, suggests that information is not lost, but is encoded in subtle correlations in the Hawking radiation. The resolution may involve deep connections between gravity, quantum mechanics, and information theory that we're only beginning to understand. Time dilation at horizons plays a central role in these discussions, as the infinite time dilation at the event horizon is precisely what creates the puzzle about when and how information escapes. Let's consider another fascinating aspect of time dilation, its effect on causality and the structure of the universe. The speed of light limit, intimately connected to time dilation, creates what physicists call light cones, the boundaries separating events that can causally influence each other from those that cannot. At any point in spacetime, the future light cone contains all events that could be affected by something happening at that point. Light signals from that event can reach any point inside the future light cone. The past light cone contains all events that could have influenced the current point. Points outside both cones are elsewhere, causally disconnected, unreachable by any signal traveling at light speed or below. This causal structure is preserved by time dilation. No matter how you boost your velocity, no matter how time dilates for you, you can never escape your light cone. Events in your causal future remain there. Events in your causal past remain there. Time dilation changes how you experience the journey through space-time, but never lets you violate causality. The causal structure of space-time has profound implications for the nature of reality. In classical physics, the entire universe exists in a single moment, the present, which marches uniformly forward. But in relativity, there's no universal present. Different observers have different presents, and their light cones determine what they can know and influence. This leads to what philosopher Karl Popper called the block universe problem. If the future exists in the same sense the past does, merely located in a different direction in spacetime, then fatalism seems unavoidable. Yet we experience choice, uncertainty, and the openness of the future. Reconciling relativistic physics with our psychological experience of time remains a deep philosophical challenge. Quantum mechanics adds further complexity. The act of measurement in quantum mechanics seems to involve an irreversible change that distinguishes the future from the past. Before measurement, a quantum system exists in a superposition of possible states. After measurement, it's in a definite state. This asymmetry might provide a physical basis for the direction of time, independent of thermodynamic entropy. But quantum mechanics also raises puzzles about time dilation. In the standard formulation, quantum events are instantaneous and non-local. The collapse of the wave function happens everywhere simultaneously. But simultaneously is relative in Einstein's universe. Does quantum collapse happen simultaneously in all reference frames? How do relativistic and quantum effects combine in systems where both matter? These questions drive research in quantum field theory and quantum gravity. The standard model of particle physics successfully combines quantum mechanics with special relativity, but it doesn't include gravity. A full theory of quantum gravity would need to reconcile quantum mechanics with the curved spacetime of general relativity, including all the subtleties of gravitational time dilation. Let me tell you about an experiment that beautifully illustrates time dilation using not particles, but actual clocks, the most direct test imaginable. In 2010, physicists at the National Institute of Standards and Technology compared two ultra-precise optical atomic clocks. These clocks were so accurate, they would neither gain nor lose a second in billions of years. The researchers placed one clock slightly higher than the other, just 33 centimeters, about a foot apart in elevation. They found that the higher clock ticked faster, exactly as general relativity predicts for the gravitational field difference across that small height. The effect was about 90 parts in 1,000 trillion, tiny, but measurable with these exquisite instruments. This experiment detected gravitational time dilation over a distance you could span with your hands. It demonstrated that every step you climb, every floor you ascend in a building, you're moving into a region where time flows ever so slightly faster. The universe really does work the way Einstein described, even in the most mundane settings imaginable. More recently, researchers have used quantum systems to test time dilation in new ways. In 2019, scientists created a superposition of an atom being in two different locations, a quantum state where the atoms simultaneously existed at two different heights in Earth's gravitational field. They verified that quantum interference effects respected gravitational time dilation, providing evidence that quantum mechanics and general relativity are compatible in this regime. These experiments approach the boundary where quantum gravity effects might become visible. If spacetime itself is quantized at the Planck scale, this quantization might manifest in subtle deviations from smooth time dilation. No such deviations have been detected, but the search continues with ever more sensitive instruments. The technological applications of time dilation extend far beyond GPS navigation. Particle accelerators rely on relativistic effects to function. At the Large Hadron Collider, storage rings must be precisely engineered to account for the increased mass and time dilation of particles, moving at 99.999999% light speed. The radiofrequency cavities that accelerate particles must be timed to nanosecond precision, accounting for relativistic effects that would otherwise desynchronize the acceleration pulses. Medical imaging also benefits from relativistic physics. Positron emission tomography, or PET scans, detect gamma rays produced when positrons, the antimatter counterparts of electrons predicted by Dirac's relativistic equation, annihilate with electrons in the body. The entire technology depends on antimatter, which exists only because of the marriage between quantum mechanics and special relativity. Nuclear power and nuclear weapons both exploit Einstein's famous equation relating mass and energy. The tiny mass difference between nuclear fuel and fission products converts to enormous energy precisely because the speed of light squared is such a large number. Time dilation is implicit in this energy release, as the processes governing nuclear reactions occur in frames where relativistic effects matter. Looking toward the future, time dilation will become increasingly important as technology advances. Any civilization capable of interstellar travel will need to account for relativistic effects. Crews on long-duration missions at high velocities will age more slowly than those who remain home. This isn't merely theoretical, it's a practical consideration for mission planning, communication protocols, and the psychological preparation of travelers who will return to futures they never knew. Some speculative proposals for interstellar travel embrace time dilation rather than fighting it. A spacecraft accelerating at 1 gravity could cross the galaxy in a human lifetime of ship time, though millions of years would pass externally. Passengers would essentially be traveling to the far future while crossing space. The destination stars they aimed for might have evolved, their planetary systems changed, civilizations risen and fallen, all while the travelers aged a few decades. Communication across such time-dilated journeys presents profound challenges. Messages sent from Earth would take years to reach a high-velocity spacecraft. By the time responses returned, the original senders might be dead, or the questions they asked might have become irrelevant. Interstellar travelers would be increasingly isolated, their connection to home becoming tenuous threads stretched across both space and time. The psychological impact of time dilation deserves consideration. Humans evolved in a world where time flows uniformly for everyone. Our social structures, our relationships, our sense of shared experience, all depend on experiencing time together. A future where time dilation is commonplace would fracture this shared temporal experience in ways we can barely imagine. Science fiction has explored these themes thoughtfully. In Ursula K. Le Guin's novel The Dispossessed, characters grapple with the alienation of interstellar travel, becoming strangers to their own societies. In Alastair Reynolds' Revelation space series, relativistic travelers form a distinct culture, moving through centuries while aging mere years, watching civilizations rise and fall like seasons. These stories help us think through the human implications of physics we might someday experience. Let's return to the fundamental question: why does time slow down as you approach light speed? We've explored this from many angles: the constancy of light speed, the geometry of spacetime, the mathematics of Lorentz transformations, experimental confirmations. But perhaps the deepest answer is that time dilation is necessary for the universe to be logically consistent. If time didn't dilate, faster-moving observers would measure light traveling at different speeds. This would break the electromagnetic equations that Maxwell discovered in the 19th century. Light's behavior would depend on how you were moving, which would mean different observers would disagree about basic physical phenomena. The laws of physics would be different for different observers. Einstein's postulate that the laws of physics are the same for all observers in uniform motion demands time dilation. It's not an optional feature that could have been different. Given the structure of electromagnetism and the requirement that physics be consistent, time dilation follows inevitably. The universe couldn't work any other way. This hints at a deeper truth. The laws of physics are more interconnected than they might first appear. What seems like separate phenomena, time dilation, length contraction, the equivalence of mass and energy, the impossibility of exceeding light speed, are all aspects of a single geometric reality. Spacetime has a particular structure, and all relativistic effects emerge from that structure. Einstein spent the last decades of his life searching for an even more unified theory, one that would combine gravity with electromagnetism and eventually with quantum mechanics. He never found it, and we still haven't achieved this grand unification. But the search continues, driven by the intuition that nature is fundamentally simple and unified at the deepest level. String theory attempts this unification by proposing that all particles are different vibration modes of tiny strings. Loop quantum gravity takes a different approach, quantizing spacetime itself into discrete units. Both approaches preserve relativity and its time dilation effects while extending physics to new domains. Neither has yet produced testable predictions that distinguish it from standard physics, but both offer glimpses of how the fundamental structure of reality might be organized. What might we learn if we could probe time dilation at even higher energies and shorter distances? Current experiments are limited by available technology. Particle accelerators can reach energies of tens of tera-electron volts, but the Planck energy, where quantum gravity effects become significant, is about 10 to the 15th tera-electron volts, hopelessly beyond current reach. Cosmic rays occasionally deliver particles with energies approaching the Planck scale, but we can't control or precisely study these rare events. Astronomical observations of gamma-ray bursts and other high-energy phenomena provide indirect probes of ultra-high-energy physics, but interpretation requires careful modeling. Future experiments might test time dilation in new regimes. Space-based atomic clocks, far from Earth's gravitational influence, could test special relativistic time dilation with unprecedented precision. Gravitational wave observations probe spacetime dynamics, where time dilation effects are extreme. The Event Horizon Telescope, imaging black hole shadows, shows us regions where gravitational time dilation approaches infinity. Each new test confirms that time dilation works exactly as Einstein described. No deviations have been found, no exceptions discovered. This remarkable agreement between theory and experiment, sustained for over a century across an enormous range of conditions, gives us confidence that we understand something true about the universe. But science remains humble about its own limitations. Every theory has a domain of validity, and general relativity surely has boundaries where it breaks down. The singularities at the centers of black holes, the initial singularity of the Big Bang. These are places where the equations produce infinities, indicating that our current understanding is incomplete. A theory of quantum gravity, when we find it, will modify our understanding of time dilation in extreme regimes. Perhaps at the Planck scale, time itself becomes discrete or fuzzy. Perhaps the smooth spacetime we experience emerges from some more fundamental structure where time as we know it doesn't exist. These remain open questions, invitations to future discovery. Consider how remarkable it is that humans, evolved to survive on African savannas, can comprehend phenomena like time dilation at all. Our brains developed to track the movement of predators and prey, to understand social relationships, to find food and shelter. Nothing in our evolutionary history prepared us to understand relativity. Yet we do understand it. Through mathematics, experiment, and careful reasoning, we've transcended our biological limitations to grasp truths about the universe that our ancestors couldn't have imagined. Time dilation, absurd from the perspective of everyday experience, has been measured, confirmed, and incorporated into working technology. We've learned to think in ways that nature never designed us for. This gives hope for further progress. If we could understand special relativity despite its counterintuitive nature, perhaps we can understand whatever deeper truth underlies it. The human mind, equipped with mathematical tools and scientific method, has proven surprisingly capable of penetrating nature's secrets. Each generation builds on the last, reaching further into the unknown. If you made this far, make sure to subscribe to the channel and give a thumbs up. And check out this other video, Why Nothing Can Go Faster Than the Speed of Light. In this video, we reveal the real science behind the universe's ultimate speed limit and why light speed is not just fast. It's the fundamental boundary built into the fabric of spacetime.